All right, okay. We continue with our discussion of the interactions of particles with matter. We've briefly already gone through the requirements on a detector. This slide is where we left off. The sketch shows a well-established compromise to achieve everything that we require from a detector with existing technology. So maybe we briefly repeat, because the interactions of photons, electrons, muons, and the other particles is what we're going to discuss now. A photon is not charged. It therefore does not leave an ionization signal. It passes through tracking detectors and leaves a shower in the electromagnetic calorimetry. An electron is a charged particle. It does leave a track in the tracking system and leaves a similar shower in the electromagnetic calorimetry. Charged kaons do leave tracks. They interact electromagnetically. They interact also strongly, which means they typically penetrate deeper and shower in hadronic calorimetry. Neutral hadrons, like kaons, for example, or neutrons, are more difficult because they don't interact electromagnetically and typically begin their shower interaction only in the hadron calorimetry. A neutrino doesn't interact at all, and a muon passes through all the detector components without showering, because it is a heavy charged lepton, heavy with respect to the electron. That means it leaves a track in the tracking system. It does ionize, but it does not produce a shower. Rather, it deposits 1 to 2 GeV or so of energy in the calorimetry. And then that's the reason why we can put the muon system outside as the last subdetector component. That is typically how detectors are organized, be it fixed target experiments or in collider experiments, because the interactions of the standard model particles with the detector material, they are everywhere the same. Now, there are two principal ways a particle can interact with matter. First, it can be consumed by a single reaction. That is the case, for example, for the Compton effect of photons. Particles can be absorbed, and that means their rate, the number of particles the change in the number of particles per unit length is constant and thus proportional to the number of particles, and hence that leads to an exponential decay. This case is therefore described by a particle number density in the detector material as a function of the penetration depth that falls exponentially. The second case is that the particle doesn't get absorbed at once, but rather continuously loses energy until it is stopped. This case leads to a different prediction for the deposited energy. The energy loss through matter of heavy charged particles, we call this dE over dx, so energy loss per unit traveling distance or penetration depth, results in a limited area with a strong drop in the intensity. That's because if you start with particles with uniform energy, it takes a calculable depth until all the energy is lost, and then all the particles thermalize in roughly the same spot and deposit the remainder of their energy there. This is exploited, for example, in cancer treatment, which we'll discuss in a little bit. You can see here an old image from 1926, alpha particles. These are heavy particles, for roughly 4 GeV and 2-unit charges, created all at the same energy from a radioactive source and penetrating a photographic plate, and one can see with extreme resolution, this is very high resolution, one can see individual tracks and how the particles are stopped after their energy has been completely deposited. And there's one track that sticks out here, which matches the energy level of an excited state in the source nucleus. So these are the two cases. Very roughly, it doesn't tell us a lot about what happens individually. So let's talk about let's talk first about the absorption of particles and rays. Consider the situation to the right. There is a box with an area F, a volume L, and inside we imagine there are scattering elements, nuclei, for example, or atoms, depending on the process, with a cross-section sigma. And we view this sigma as a geometric cross-section, so as, for example, the diameter of a hard ball from which the incident particles are either scattered or penetrate. So the detector volume is V equals surface area times length, with a number of particles nt. Now let's do a small calculation. Maybe I try to write here. The particle, let me give you an example of this. I'm trying to annotate. I've tested it before, it should work. The number of target particles is the density, I'm just copying the formula, the density times the volume divided by the molar mass times Avogadro's constant. To give you an idea, I use a few, we use numbers. We compute the number density, that is the number of target particles per unit volume. So this is, of course, given by the formula above. Density times Avogadro constant divided by the molar mass. And let's use the numbers for iron because it's a material that's often used in detector applications. So I take the density of iron, 7.8 something gram per centimeter cubed. And we divide this by the molar mass of iron, gram per mole. Oh, it doesn't seem to work. And multiply with Avogadro's constant. My pen stopped working. Let me clear. Avogadro's constant, so this is what we had before, times, okay, I'm sorry, the pen is not working. Let me, anyway, share my screen. So I hope you can see this now, and actually I hope it can work. Something is not quite right here. Okay. I'm sorry, we need to do without the pen. Maybe it's not so important because these actually are only. Let me get back here. So inserting the numbers that you saw. Am I sharing now? Wait, let me see. I am sharing now again. I'm sorry about this. I try once again to annotate something. No, it doesn't seem to work. Okay. So, using the molar mass of 55 gram per mole, we can easily compute the number density. Unfortunately, I have to say it in words. That's a bit less than perfect. Of 8.5 times 10 to the 22 molecules of iron per cubic centimeter. Now, for a thin absorber, my mouse cursor is gone. For a thin absorber, the cross section is. Wait, I need to. Okay, I'm restarting. Okay, for a thin absorber, the cross section of that the incident particle sees is just the particle density times it's just the particle number times the cross section the particle sees. That's the definition of thin. So imagine a particle coming from the left. Per unit area F, it sees just the number of particles, the number of particles inside that volume times sigma. That's the definition of thin, because this is no longer valid if the particles shadow each other. So the definition of thin is that there is no shadowing of particles if for the incident one. In that case, we can compute the probability of a scattering event in two ways. The first way is to take the rate of outgoing scattering events per unit time and divide it by the ingoing rate of particles per unit time, because that number will give us the probability that the scattering event actually happens. We can also compute this geometrically as the total area, the total cross-section area the incident particle sees, which we've just explained is the number of particles times the cross-section here of the individual particle, and divide that by the unit area. If we insert the number of target particles as given above here, we find that this is n, the density, times sigma times L. And inverting this gives us a nice formula for the cross-section. So we can measure the cross-section from the ratio of outgoing to incoming particles, which is the probability of a reaction. And then we divide by everything this outgoing rate scales with, which is of course the total number density of scattering elements, n, and the depth of the thin absorber. So with this formula, in general, we can compute the cross-section from simple counting experiments if we know the geometry of our scattering element and the density of the particles in the scatterer. Now, for a thick volume, where we have many such layers behind each other, there is a simple differential equation, namely the relative change of the relative change in the total number of particles that go in is of course minus n times sigma times dx, which is just a different way to express the probability of a scattering event to happen. Integrating this equation leads to, I'm sure everybody can do that, integrating this equation leads to an exponential and falling exponential with a parameter mu, and mu is the mean free path, which is mu is the inverse of the mean free path and is 1 over n times sigma. So from the cross-section and the particle density, we can very easily compute the mean free path of a particle that it can travel to subsequent layers of scattering scattering elements in the setting as described in this sketch. Typical values for the cross sections are the following. The nuclear cross section is very roughly the size of the nucleus, and then the size of the nucleus more or less scales with the atomic number. So if you take a Fermi and if you take a Fermi scale times pi and nuclear number to the power of 2/3, one gets very roughly 45 millibarn times a to the power of 2/3. For proton-proton collisions, we already explained earlier that it's actually 80 millibarns. So for very low numbers of a, this is not the best approximation. It's a factor of 2 off. Atomic cross sections, on the other hand, are enormous. That's of course because an angstrom, the typical size of an atom, is much larger than a Fermi, which is the typical size of the nucleus. They are roughly 5 orders apart, and because the scale enters squared, it is more than 10, or it's around 10 or so orders of magnitude difference. So for atomic cross section, we talk about 10 to the 8 barn, which is a very large number. Now, let's talk about the interaction of charged particles with matter in a little bit organized fashion. So when we now imagine a charged particle going through a material, there are several interactions that can take place. The first one is ionization. Ionization or excitation of detector material. So think of a muon or an alpha particle or any other heavy charged particle. It will Rutherford scatter, Coulomb scatter, the electron with electrons in the in the atomic shell, kick them out, and thus lose the energy. Thus lose its energy along the way. Then it can interact in a similar way with the nucleus. If the particle is deflected in its interaction with the nucleus, it is accelerated, so it may also emit photons. This process is called Bremsstrahlung, which is an English word, because 100 years ago, the language of physics was actually more German than English. So Bremsstrahlung are the photons that are emitted if a heavy charged particle is deflected at a nucleus and thus accelerated. This is the synchrotron radiation equivalent that we have already calculated, and we're going to use the formula again. Then it may happen that the particle travels through the medium where the velocity of the speed of light in the medium is lower than the velocity of the speed of light in a vacuum. So if the particle has a high beta, high velocity, it may actually travel faster than the speed of light in the medium. Quite similar to the pressure shock waves that supersonic jets produce, it is then possible that a shock wave of light manifests itself, and this shock wave of light can produce ring-like structures in detectors, which is called Cherenkov radiation. And finally, the particle may traverse boundaries between two refractive media where the speed of light changes because the material properties change, and because the electric field in the vicinity of the traveling particle has to change according to the Maxwell equations in matter, and because the material properties change, it has to rearrange itself while it traverses such a boundary. And in this process, X-ray photons can be emitted. These are called transition radiation. Now we are going to talk about ionization a lot because it's important. It's the core principle of the signal detection, the signal creation, I'm sorry, and detection. We'll talk a little bit about Bremsstrahlung. It's mostly relevant for the lighter particles because, as before for the synchrotron radiation, it is strongest when the particle is light, and the lightest charged particle in the standard model where this is relevant is actually the electron. And for Cherenkov and transition radiation, we'll only do a qualitative treatment because these are a little bit less important. So now I have to fix my iPad, Rechnen vollständig verstehen kann während der Vorlesung. Okay, so we now calculate the energy loss of a heavy charged particle while it goes through a detector material. First, we need to make a preliminary calculation of the maximum energy transfer that can happen in such a collision. What collision are we talking about? Think about a muon or an alpha particle or whatever, and it is now traveling through matter. So there are atoms and there are electrons in the nuclear shell. Kicking out these electrons, that's what we call ionization. And in fact, this is Rutherford scattering, but in a different rest frame. In Rutherford scattering, we had a lighter particle being scattered at the Coulomb potential of a heavy nucleus. Now we have a heavy particle, not saying that's a nucleus, it can be, but it need not be, it can also be a muon, and it is scattered at the electron in the nuclear, in the atomic shell. So we first write the energy momentum conservation for the initial and the final state. The heavy particle is capital P and the electron is lowercase pe. So P plus Pe equals, of course, P prime plus Pe prime. And that equation, the first thing when you see such an equation is you can square it to find out Lorentz invariant relations among the Lorentz invariants. So we do this and we find P squared minus P squared plus 2Pe equals Pe squared. And on the other side, we find P prime squared plus 2Pe prime P prime plus Pe prime squared. The squares all go away because of the masses, and we are left with P in Pe prime equals P prime minus Pe. So this equation, the squared equation written here entails property. It entails that the in products of the final state, the four vector momentum in product of the initial state heavy particle and the outgoing electron momentum is equals the outgoing heavy particle momentum times the ingoing electron momentum. Good. So we know a few things about these momenta. For example, we can neglect the initial state electron kinetic energy. We say that the electron is a 4-vector only with a zero component MEC squared, but it has no initial momentum. Similarly, so this makes the right-hand side here very simple to compute. It's just the energy of the outgoing particle times MEC squared. On the left-hand side, we take the zero component, which is the product of the two energies of the ingoing heavy particle energy and the outgoing energy. And then there is the typical, then there is the product of the momenta with the typical cosine theta, where the cosine theta is the angle of the outgoing electron with respect to the incoming heavy particle. So it's the angle by which the electron is scattered away. Now one can solve this equation trivially. It's cosine for cosine theta, and that's what is written here. Now one need to take a few steps that are all simple. Each one of them is simple, but as usually in special relativity, you have to know exactly what you're doing. Otherwise, you fill pages with formulae that are correct but useless. So the correct and useful definition is the kinetic energy of the outgoing electron. It's a relativistic kinetic energy, so we take EE prime, the energy of the outgoing electron, minus the rest mass, MEC squared. It then directly follows that the energy E of the ingoing proton, sorry, I'm always saying proton, it's not true, the ingoing heavy charged particle equals the two energies, the sum of the two energies, E prime of the outgoing heavy particle plus the kinetic energy of the electron, because the rest mass of the electron was already there. So we can now therefore express the energy of the kinetic energy of the electron in the following way. We take the energy momentum relation of the outgoing electron, which is just EE prime squared equals C squared PE prime squared plus ME squared C to the fourth, and we solve this for the momentum squared. So we compute the magnitude of the outgoing electron momentum. It is the outgoing electron energy minus the rest mass, but we've just used this definition to define the kinetic energy, so we can rewrite the magnitude of the outgoing electron momentum in terms of its kinetic energy, and it becomes T squared plus 2MEC squared times T. We take the square root, and that's it. Inserting this equation into cosine theta, it is two manipulations that I would like to have done, with my pen and show to you in detail. But all you do is now CPE prime and the definition of T are inserted in the expression for cosine theta. There are 4 terms appearing in the numerator. However, this term here, the MEC squared times gamma, it cancels with the energy of the ingoing heavy particle, because the energy of the ingoing particle is also just gamma m c squared. So these two terms cancel, and we are left with 2 terms as a function of, so 2 terms that contain the kinetic energy of the outgoing electron times the gamma factor, and that's the gamma factor of the particle that travels through matter, plus constant terms, functions of the masses, and divided by beta gamma and square root of T squared. Now, that's an equation, that's a quadratic equation now for cosine theta. we now invert this quadratic equation, and that's something I wouldn't have done anyway, because I believe you can all solve quadratic equations. So we solve this equation for the kinetic energy in terms of the angle. And the result is given here. And it looks like a complicated formula, and it probably is, but what does this formula tell us? It gives us the energy transfer from the ingoing heavy particle to the electron, because it is the kinetic energy of the electron in the final state, and it started with 0 and it ends up with t. So that's the energy transfer, and it's the amount the traveling heavy particle loses per interaction. And it depends now on the scattering angle theta. This formula you don't have, of course, to learn by heart, but its limits are very interesting. First of all, the maximum is achieved for cosine theta equal 1, which means that's head-on scattering event. So when the heavy particle is in the same, hits the electron head-on, then we have maximum energy. Then we have maximum energy transfer. If we do so, T max, the maximum energy transfer, is given by this more simple formula, which we can now look into for different cases. First of all, you see in the denominator there are 3 terms. And for each of the 3 terms can become important. First, we consider the case when the gamma factor is not very high. In this case, if the gamma factor is not very high, and not very high means that the gamma factor of the particle that goes through the matter times the electron mass is way below the mass of the parent particle. In other words, the mass of the electron in the rest system of the heavy particle must be much smaller than the mass of the particle itself. In yet other words, this just means the particle must be massive enough and have a high enough momentum that it can just easily kick out the electrons from their shell. In this case, the formula reduces to the numerator, and you see that in this case the maximum energy transfer is given by beta times gamma, and beta times gamma is the crucial momentum dependent function that drives the energy loss of the particle in the medium. So everything we're going to compute, most of what we're going to compute, will be a function of beta times gamma. Now, you can also look into the limit of an ultra-relativistic heavy particle. In this case, the energy transfer, so gamma goes to infinity. It's only the middle term here that is important, and one of the gamma factors cancels, and the maximum energy transfer is then just gamma times m times c squared. That's a very interesting and very important result, because it means that if the incoming heavy particle is moving relativistically, it can in principle transfer its whole energy on the electron. It will rarely happen, but sometimes with a low probability, it is possible that the energy transfers are extremely large. Good. So we have now computed the maximum energy transfer for these 2 different cases. The third one is when actually we're not dealing with a heavy particle, but with a light particle, the electron, and then it takes 2 more steps to this ratio in the bottom, me over m, is of course 1, and then you can cancel the resulting beta squared and gamma squared factors to arrive at gamma minus 1. And that just tells you that you can also in this case transfer the whole energy to the electron. We're not going to use the last case, it is given here for completeness. Now, that was the calculation of the maximum energy transfer. Not a lot has happened. Now we need to talk about energy loss by ionization and integrate our, perform the different steps and integrate up all the energy losses from all the electrons in a given slice of material the heavy particle is traveling through. In the following, I'm going to give Bohr's classical result that he obtained more than 100 years ago, and it is the Bethe-Bloch equation. The Bethe-Bloch equation governs all ionization signal creation processes in detector physics. It's extremely important, and the derivation is very worthwhile. It's classical and it's rather simple. Now, I will try a last time my stupid pen. No. For some reason. It doesn't work. Okay, so in the following we give Bohr's classical results. We have now a particle with charge Ze, and remember this is a lowercase c, with mass capital M and velocity v. It travels through a medium with a certain electron density Ne. We've calculated the energy density on the previous slide. Now we consider on one of the previous slides. Now we consider the electrons free and initially at rest. So they have a particle with mass m, some gamma factor is dependent on its, as a function of its velocity, and a charge c times e travels through matter and sees essentially these atomic shells with electrons free and initially at rest. The momentum, now we compute the momentum transfer to a single electron. The momentum transfer is only computed in the plane, in the direction normal to the direction of movement. It's not computed in parallel because the parallel momentum transfer is zero. If the charged particle approaches, it does in fact transfer some energy to the electron in the shell, but once it has passed, it gets back this energy, because in the second half of the movement, when the heavy particle has passed, the particle is on the other side, and first it decelerates and then it may accelerate, depending on the relative sign of the charges, of course. Long story short, the momentum transfer in the parallel direction of movement is zeroed by symmetry arguments. Now, let's look at the transfer of momentum to the electron in the from the heavy particle to the electron in the perpendicular direction, and we write this as a force integral over time. Over the time the interaction takes place in our simplified setting from minus infinity to plus infinity, and we introduce the velocity here to have the inverse of the velocity here, to write this as a spatial integral. So we need to know the velocity and we need to know the force in the perpendicular direction. So let's compute the force in the perpendicular direction. This is done using Gauss law in SI units. Gauss law is telling us that the integral of the transverse direction over a cylinder equals the charge, the total charge that's inside that cylinder. So imagine there's an electron here. Imagine there's a charged particle here. We draw a cylinder and we call the distance of closest approach, as usual, we call this the impact parameter. We give it a name B because that's a quantity that will come back in the following steps. So we have a heavy particle with velocity v passing by, and now we compute the total momentum, and now we are at the step where we calculate the force in perpendicular direction in this process. Now, Gauss law times the radius of the cylinder times the integral over the x-axis equals the total charge in the cylinder, which is given by, as we said, C times E over epsilon 0, and the epsilon 0 is from Maxwell equations in SI units. Now that means we can compute at least we can compute the total integral of the perpendicular E field as a function of the impact parameter. So if we are close, this integral of the transverse component is very large. If you're far away, it is much lower. We can use this to compute the transferred momentum. We simply insert this integral. We can simply insert this integral here and assume that the velocity is constant in the process. So there are all sorts of simplifying assumptions. But it's a classical derivation, and eventually we get very close. Now, inserting here means that we can express the momentum transfer as C times E squared over 2 pi epsilon 0, with the 2 pi coming from the integral in the angular integral of the cylinder, divided by the impact parameter and the velocity. And from the momentum transfer, we can compute it's non-relativistic, but we compute the energy transfer. So the energy transfer is just delta p squared over 2me. And what you get to do now is take the expression for the momentum transfer, insert it in the electron transfer, in the energy transfer to the electron, and simplify the constants. So before we do that, we take it one step further, because that was the transfer of a single electron, and now we need to integrate this transfer over a shell of thickness dB, a length dx at an impact parameter b. That's the integral that we are doing. And we take, that's the integral we are doing, and the number of electrons that are distributed in this spiral is just the electron density times, of course, the circumference 2bb times the thickness of this, the thickness of the barrel times dx, the length of this element. We insert this. We put now everything together, and we compute the energy loss. That's why it gets a minus sign. So that's the energy loss of the heavy particle that's going through here. It is the delta p squared over 2me, which is computed, and multiplied with this barrel volume element. If you put things together, you get NEC squared e to the 4th divided by 4 pi epsilon 0 squared me times v squared. And the important dependence is dB over b times dx. Now, there was one cylinder element. Of course, we're not interested in a cylinder. We are interested in the energy change per unit length x. So we need to integrate over the impact parameter. And that's the impact parameters of the different interaction of our heavy particle with the electrons. Now we integrate from some minimum to some maximum impact parameter. Why are we doing that? We are doing that because that integral is actually not finite. You cannot integrate 1 over b from 0 to infinity. It diverges logarithmically. So if we take some fixed up, we take some boundaries, b in minimum and maximum impact parameter, and vary about the boundaries later. So we get an equation with, we get our numerical prefactor. Importantly, watch out, there is a factor 1 over velocity squared, which gives a beta squared in the denominator. So this is one important result of our calculation that is already apparent now. This is 1 over beta squared term. And then it gets multiplied with the logarithm of the ratios of the minimal and the maximum impact parameter which take place. Now, there are a few simplifications that we've done. You may have seen there's an RE appearing here. RE is the classical electron radius. The classical electron radius is a constant of nature that's defined by the radius where the electrostatic potential of a charge of size E equals the energy that's needed to create an electron itself. In principle, we call this the classical electron radius because below that radius, we are sure that we are in the regime of quantum field theory and quantum theory, because the energies are then below the distance, they are high enough to create new electrons. For us, that's not important. We just call this the classical electron radius, and because we want to get rid of the epsilon zero. The epsilon zero is depends on the conventions, and we don't like it. MEC squared doesn't, and so we use that. B is now the impact parameter in a single particle interaction, and B min and B max give essentially the range of these ionization interactions that we have to consider. As we said, none of these values can be 0 or infinite, because in that case the total stopping power of the material for the charged particle would be infinite. So we have here a very simple equation in principle, and the complexity comes now from considering which of the individual ionization interactions actually have to be considered. Here is where our work on the maximum energy transfer pays off the most. Remember that we had a limit for the maximum energy transfer T max of 2mec squared beta squared gamma squared, which was valid in the which was for the non-relativistic case, here defined by the effective mass of the electron in the rest frame of the heavy particle, but that's a detail. The point is it's 2mec squared beta squared gamma squared. So this beta squared gamma squared appears now in our equation for the energy loss. How does this go? The maximum energy transfer at the minimum distance. So we have to say that the maximum energy transfer happens at the minimum distance. Okay, this is what we computed before. It was delta b squared over 2me, and we insert this, and because the impact parameter appears in the denominator, that was our previous result, we know that at the minimum distance for head-on collisions, we have the maximum transfer. And all we need to know is that T max is proportional to 1 over b squared, 1 over impact parameter squared minimum. With that knowledge, we can do the following. We can say the logarithm of the maximum to the minimum impact parameter that we have to consider is 1/2 times this thing squared. So it's Bmax squared over Bmin squared. But there is a Bmin squared in the denominator, and that is proportional to the Tmax. So we can actually take this Bmin squared in the denominator and replace it with a Tmax, and we do it vice versa. The Tmax is the maximum energy transfer in individual collision, and we have computed it before. It was 2mec squared beta squared gamma squared. The other question is, so that's the maximum energy transfer. It happens if the heavy particle hits the electron head-on. The other question is, what happens to the minimum energy transfer? What's the minimum energy transfer? And here we cannot do a classical calculation, because classically the energy transfer to an electron can become arbitrarily small. If you have a muon passing through your room, and you surely have muons passing through your room right now, although you can't see them, you can actually calculate the energy transfer to an electron in an atom on the moon. It's going to be small but non-zero. On the other hand, you know that the atoms on the moon and everywhere, they have material-dependent ionization thresholds. So there is no energy transfer possible due to the quantization of the energy levels in the material that the particle is traveling through. And below the lowest energy level, no energy transfer is possible. Hence, we replace the minimum energy transfer by a material-dependent quantity, which is the ionization threshold. This material-dependent quantity can be measured. Usually, it is measured and averaged, because we have compound materials. We rarely build detectors from a single atom. Detect the material from a single atom. On the other hand, there are also quantum mechanical calculations for this ionization threshold. There are papers appearing on this in the relevant journals with hundreds of pages of calculations. We use typically tables for that. So all the low energetic quantum mechanic processes that lead to ionization, that lead to the determination of the lowest ionization threshold are relevant here. And if even below that, you have to consider that there are interference effects from the different electrons in the shell that will then further, and shielding with the nucleus and so on, that further would reduce the interaction at low momentum transfer to negligible levels. Good. We have to do one more thing. We substitute the electron density. That's the exact same formula that we had before. I would have liked to give you a few numbers, but I'm skipping that for next time maybe. The electron density is the density of the material divided by the atomic mass, multiplied with Avogadro's constant. This is just the number of atoms. And if you multiply the number of atoms with the atomic number C, you get the electron density. The electron, using this expression for the electron density for the total number of electrons, now finally makes us arrive at the final result. Minus the E over the X equals a constant of nature, which is 4 pi times Avogadro's constant times classical electron radius squared times MEC squared. This is a constant of nature with a value of 0.300 MeV centimeter squared per mole. It's not very useful, but as is, it is useful once you multiply this with the density of the material. Whoops. Because then you arrive at the typical values for the energy loss. We discuss this on the next slide. The next thing are the prefactor gives you the size, the typical size of the energy that you're losing. The second term, the 1 over beta squared, tells you that the energy loss is very large at low velocities. Then there are factors C and C squared. That's the capital C is the number of is the atomic number, so it's the number of electrons per atom in the target material. And here it tells you that these are incoherent scattering events. The heavy particle interacts individually with one electron and the next electron. There's no coherence between the electrons, otherwise it would be C squared. So this dependence, this linear dependence on the atomic number is very important and is different for other processes of heavy particles in matter. And then of course, because of the coherent interaction, in case there are more than one charges in a bound state of the in the hypothetical bound state of the incident particle, you get the C squared here. Think of an alpha particle. An alpha particle will have two protons separated by Fermi. This will lead to coherent interactions, and hence there enters a C squared. And the classical calculation takes care of that, essentially because we have identified the electric field proportional to C, and the energy is the energy transfer becomes the square of that. And then there is our logarithm, and the logarithm is the ratio of the kinetic maximum energy transfer formula divided by the material property of the material property describing the minimal ionization threshold. So the reality is only slightly more complicated. We've treated Rutherford scattering classically. One has to do this in quantum mechanically, and at some steps we've used non-relativistic approximations, and this has to be done relativistically. The full derivation is too complicated and doesn't tell you a lot. The end result is here. It's exact that the leading term is the same, except there is an extra factor of T max over I. If you look here, we only had the T max over I, and here's another T max and a square. And then there are a few corrections. The 1 over beta squared is still here. The crucial dependence on the capital C, which is the atomic number of the target material, and the number of charges in the heavy particle, is exactly correctly described because the classical term is the leading one. And then there are different corrections. This beta squared here, let me show you the full slide. The beta squared here is a correction from the spin 1/2 interactions. It's only there if if we talk about the spin 1/2 interaction, and then there are corrections from the finite extent of the electromagnetic field in the medium. So that's a delta of beta gamma, and then there are more complicated shell corrections. Those are tabulated. They are numerically small. We will not consider any of these. We just look at the basic properties. Now, the prefactor is constant of nature, as we said. By the way, the electron radius is 2.8 Fermi. So if you get closer than that to an electron, you have enough energy to create another electron. Good. Prefactor is constant of natures. Then come the properties of the incident particle, its charge, its beta, and the relativistic gamma factor, and then a bunch of target material properties. Now, that's the formula. Here is a logarithmic dependence divided by 1 over beta squared. This is what it looks like. Here is the EDX divided by the density, which is often done. So the unit here, so you divide the row that's appearing here, you just divide it, and you show the EDX over rho in units of MeV centimeter squared times gram. If you multiply this with gram over centimeter cubed, you immediately get MeV per centimeter, and that's the energy loss of a heavy particle per unit area in a material if that beast has a beta gamma of a certain value. The crucial dependence is the 1 over beta squared term here that tells you at lowest momenta, particles very quickly thermalize. And at high momenta, you have a logarithmic beta gamma rise. Now, the dashed line is our calculation, the one that we have gone through. The density correction, the delta beta gamma density correction, brings you down to more realistic level, predictions. It's not a small correction. It's mathematically complicated, and we don't learn anything. It's also material dependent. But I want to tell you that it is necessary to include it. However, the main features remain. Per unit, per gram per cubic centimeter, we use 1 to 2 MeV per centimeter. Okay, so we talk about for a density of 1 gram per centimeter, you lose 1 to 2 mega electron volts from ionization. If so, at least at the minimum here. This grows with logarithmically if your momentum increases, and it grows with 1 over beta squared at low momentum. The example we're showing here is pions on silicon. Pions on silicon is the most important example at the Hadron Collider, because silicon detectors are tracking detectors are silicon detectors, and tracking detectors are the first detectors next to the interaction point. And pions are the most abundantly produced charged particles, and hence pions on silicon is the interaction in the signal generation process that's the most abundant for real life applications. The minimum is achieved at beta gamma at the beta gamma value of between 3 and 4, because beta is roughly 1 at these values. It's actually the gamma factor. To make it more concrete, if you invert this, the minimum is at beta equals 95% of the speed of light. These particles are called minimum ionizing particles. The energy loss of those particles the energy pions of 95% of the speed of light lose the least to ionization. That's important because it also tells you what in your typical detector application, imagine you have a complicated jet and each shower, they produce plenty of particles. Deep in the detector, what's the typical energy of a particle that you encounter? Now, the particles may be created with very high energies up here, and then they lose, and because they lose, their beta gamma factor reduces, and then they lose a little bit less. Eventually, they roll down into this well, and where the minimum ionizing particles, and at this point, they stay the longest, and they stay the longest because they lose the least amount of energy. But they do lose a little bit, and once they've lost a little bit more, the 1 over beta squared term takes over, and they are stopped. That's what we've seen in that's what we've seen in the picture of the photographic plate from the alpha particles. Ionization is the universal detector principle for semiconductors, for gaseous detectors, and many more. We're going to discuss detector principles in the next few lectures, and most of the signal generation will be ionization. Let's take an example. I would really like to calculate this for you, but it's not, I need to fix this somehow. It does not work now. Iron with 7.87 gram per centimeter cubed. The loss of a minimum ionization particle is 11 MeV per centimeter. So if you have a muon, for example, it loses only 11 MeV per centimeter. The EDX in the regime of the 1 over beta squared term and the log gamma rise is called the beta Bloch equation, and this energy regime, this momentum regime, is called the beta region. There are for much lower momenta, once the particles have thermalized, there are different corrections and effects that change the behavior. But all in all, over 9 orders of magnitude, the stopping power of material on heavy charged particles is known and very well described. So once again, a 1 over beta squared term, a minimum ionization region at the beta gamma of roughly 3 to 4, then a log gamma rise, and then at the very highest energies, what we've not so far discussed, you get radiative losses from Bremsstrahlung. But Bremsstrahlung effects for muons only enter in the TeV regime. So here we have 1 tera electron volts. That's about the highest momenta of muons that we can create and detect at the LHC experiment. So for muons, these radiative losses are not practically important. It's we talk about at most 100 or hundreds of GeV, but those are not really large. The beta treatment, as we've done, is accurate from a beta value of roughly 0.05 all the way up to beta gamma values of several hundred. One definition that's not so important for muons, as we said, but for electrons very important, is the critical energy. The critical energy is defined as the energy of the heavy particle where the radiative losses from Bremsstrahlung equal the ionization loss. So above the critical energy, ionization is a subdominant process, and Bremsstrahlung is more important. But really, the life of a detector physicist is in the Bethe region for the most part. Let's look at some materials. It's interesting to compare. I think it's interesting to compare materials and particles. Now, the plot to the right has an enormous amount of information. First of all, the EDX is divided by the density, so you can compare liquids and gases, which have very different densities and hence very different energy loss per unit area. But if they are normalized to the density, this leading density effect drops out, and one gets very similar shapes. So these are always the 1/β² terms with different, slightly different, only very slightly different beta gamma values for the minima, and then the log gamma rise. We have here low Z materials, helium with a Z of 2, and then we have carbon, aluminium, iron, tin and lead. So the energy loss falls roughly with the average energy loss increases linearly with the number of electrons per atom, with the atomic number C. Compare the different momenta. The Bethe-Bloch energy loss is given in terms of beta gamma. Beta gamma is just the momentum in units of the mass. So you can read off the energy loss for muons here, for pions and for protons. Now, because a proton very roughly has 1 GeV, beta gamma equals more or less, with good accuracy, within a few percent, it equals the proton momentum. Now, at the same proton momentum, the energy loss for a muon of the same momentum will be higher because it has a higher beta gamma at the same momentum. So a 10 GeV proton will lose less to ionization than a 10 GeV muon if for the materials shown here, because we are in the regime where the logarithm rises here, and the beta gamma factor is higher for a lighter particle, and similarly for pions and for all other particle species. One thing you may note is that liquid hydrogen sticks out. It has a much higher energy loss, but that's because we talk about density normalization here. And the number of protons per unit density is highest for hydrogen because hydrogen has no neutrons. That's all. That's the reason why hydrogen is higher here. Helium has a ratio of C to A, so atomic number to nuclear number of 0.5 because it has 2 neutrons and 2 protons. So because it is density normalized, hydrogen sticks out a little bit, but because the ratio of protons and neutrons is in the 0.5 ballpark, you can very well compare the rest of the materials. Good. Most of the shapes are very similar. If you look at helium, you see a slightly larger increase here. It has a slightly different behavior. The reason for this is a density correction in gaseous helium, because the transverse reach of the electric field is finite. We're going to compute that. I hope I can do that today. And hence, gaseous materials have a slightly different log energy rise. So that detail will be better understood with a calculation we hopefully do in the next lecture. let's look finally at the minima, the minimum ionizing particle minima. They are very close. All of them are very close for beta gamma values of 3 to 3.5, and that extends for materials that are shown here for atomic numbers of between 7 and roughly 100. So this is really a very universal equation. The Bethe-Bloch region is really very universal, and with basic scalings, with the atomic number, the momentum, and the mass, one can ballpark compute the energy loss due to ionization within a few percent. That's why it's used so much. Let's make a simple example. Let's see. The object to the right is the CMS experiments magnet. It is roughly 50 centimeters thick, and it consists completely of iron. This is the largest superconducting magnet being operated in the world. It's 2.5 meter long and 6 meter in diameter. So the diameter is roughly 6 meter. It's also cooled to 4.7 Kelvin, and it provides our 3.8 Tesla magnetic field. Outside here is the return yoke, consists of iron, and the magnetic field outside here is roughly 2 Tesla. So these are very large and thick metallic structures. Now, let's say a muon is created inside, and we had our sketch on how to detect particles. In the beginning of the lecture, I said that muons traverse the whole detector without much interaction. Now let's check whether that's true. Let's say we have a W boson that has 80 GeV. Let's say it decays to a muon. The muon, let's say, has 50 GeV. So 50 GeV of transverse momentum. And now let's calculate the energy loss. The energy loss in, the energy loss of a 50 GeV muon, I really would like to do this by hand, but let me do it with the mouse, so we are roughly here at the muon momentum 10, 20, 30, 50. We look at iron, so we are here in this diagram. So we read off 2.2 MeV centimeters squared per gram, multiplied with the density of steel, 7.87 gram over centimeter cubed, and multiplied with the thickness of 50 centimeters. So let's compute the energy loss of the magnet. And it's 0.86 GeV. That means we have a few percent losses here, okay? Because we had 50 GeV, we roughly lose more or less 1.7, 1.6% of the energy of the muon when it traverses this 50 centimeter magnet that consists of steel for the most part, some aluminum, and of course the superconducting material. That's what we mean that's what we mean when we say that a muon can traverse the detector. So if there are very thick steel structures, we may lose a few percent, but still is very impressive and is modern enough to have a muon momentum measured accurately outside. One more thing, well, let me go back. You see here the different axes. The proton momentum, the pion momentum, and the muon momentum, if they agree, because of the different masses of these particles, they lead to completely different beta gamma factors, of course, because it's a momentum per mass. That means the energy loss is different for different particle species. And that's exploited, for example, in time projection chambers. The EDX energy loss, the Bethe-Bloch energy loss, can be used to identify particles. What's shown left is the time projection chamber of the Alice detector. It's operated with a gas, so the energy loss is small. The plot to the right shows the EDX measurement in lead-lead collisions. So these are really violent many particle collisions. You see an event display here. It's crazy. This is thousands of tracks. The time projection chamber would barely fit into our lecture room had we done the lecture in person. It's 3 meters in diameter, and I believe it's 6 to 8 meters, something between 6 and 8 meters long. It's really an absolutely gigantic gas field monster that can be read, that is read out in a microsecond time scale. So you cannot read out every collision with that. But if you read out a collision, you get all particle tracks simultaneously, and now you can also identify those particles. Why can you do that? Because you can measure the momentum from the curvature of that track. You know the momentum, and you know the energy loss. And if you know both, you can make a two-dimensional map. And because the beta gamma factor that enters the energy loss is different, the different particles populate different branches here. So we have electrons and pions here. For those guys, actually, it's Bremsstrahlung that's most important, but kaons, antiprotons, anti-deuterium, anti-tritium. This is not the top quark, this is anti-tritium. Anti-helium-3 and even anti-helium-4 can be identified. It is the first man-made creation of anti-helium-4, and I believe it was the first time that anti-helium-4 was even was observed. So it was man-made, produced, and it was observed. This is second observation of anti-helium-4 in cosmic radiation by the AMS experiment since a few years, but I think this was in 2010. This came first. So here we have anti-helium-4. This is a crazy nucleus, a completely antimatter. There are 12 antiquarks in there. 12. I find this really bizarre. So we're creating antimatter. And this antimatter is identified by its energy loss, in this case's detector. I think that's absolutely great. Now, with this success story, we're now going to talk about limitations. Truly, one also has to step back and think about what is happening here. I mean, we collide lead nuclei. Those lead nuclei, there are hundreds of collisions taking place the same time. Thousands of tracks are produced. Those tracks are read out from the time projection chamber simultaneously, and from the curvature and the energy loss per unit length that we do understand so well from the calculation we've done, we can identify objects that consist of 12 antiquarks. So remember angels and demons. This is really it. So here we have, I think it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 10 anti-helium nuclei. That's great. That's really antimatter. Okay, but now let's talk about the shortcomings. Because the energy loss has very unfavorable stochastics. Look at the spread here. The spread of the energy loss is actually significant, and all the way down here, those energy loss regions per particle, they overlap, and we cannot tell the particles apart anymore. So in principle, we would like to reduce this spread and to make a better measurement. But this is really limited, and the limitation is a core physics principle that limits much of detector detector signal generation, and that's what we discuss now. We now discuss the stochastics of the energy loss. We have already discussed the mean values, and now we discuss the spread. That's not something where I will do the calculation by hand. It's very complicated. It took a Russian to compute it, Landau. What are we talking about? The Bethe-Bloch equation, it describes the mean energy loss. If you read up the PDG live review of particles in matter, which comprises the whole field of particle physics, one of the first lines says, few concepts in high energy physics are as misused as the EDX. Look at why is it so? Look at the bubble chamber from the bubble chamber photograph from 1958. That's with liquid hydrogen. We had the liquid hydrogen line on the previous slide. This was, by the way, used to discover the omega minus, which was predicted by Gell-Mann when he introduced the quarks. The direction is here bottom up, and you see heavy particles going through that material, and you see these curled trajectories are electrons that are kicked out, and they cause secondary ionization. What's happening here is that we have ultra-relativistic particles. If we go back to our formula of the maximum energy transfer, and now that's exactly why we've calculated it. So the maximum energy transfer has the general formula here. If you take gamma to infinity, you have to take beta to 1. You find a cosine in the numerator, and you find a sine in the denominator, because this beta squared becomes 1. And hence, the maximum energy transfer as a function of the angle of the scattered electron goes with 1 over tangent squared of theta. That means that for head-on collisions, the energy transfer can become extremely large. Of course, we've taken gamma to infinity, so this can also go to infinity. Gamma cannot realistically be infinity; it can just be very large. But as a function of the scattering angle, you see a 1 over tangent squared theta behavior here. That's very bad. So for head-on collisions, the energy transfer is huge, and otherwise it's small. That means we get distributions that are very difficult to handle. In a thick absorber, we will get a roughly Gaussian distribution, because on average these effects cancel, and they happen on average with the same rate, and so you become something that resembles a normal distribution. However, in thin detectors, sometimes you have very large energy transfers, and other times they are not as large, because the probability that such an extreme reaction happens that produces secondary ionization is very low. And if you look at the picture, if that's your silicon sensor, then one of these guys had a very violent interaction, kicking out a secondary electron, producing a huge signal, and all the other guys, they just had a single track passing through, so depositing much less ionization signal. These large fluctuations, as I said, are mathematically hard to handle. Just to give you an idea, you don't have to learn this, of course. The distribution is given here. It's this integral formula. It's the Landau distribution, and it is a heavy-tailed distribution. With heavy-tail, we mean it's a distribution with a mean value or an average that is low, and then for large values, it does not fall off very quickly. It falls, but slowly enough that we cannot neglect this tail. In a few percent of the cases, we get a much higher energy loss than we get on average. So here, in this particular case, the fractional energy loss is a few percent, let's say 8, but sometimes it's 20%. And if the energy loss is sometimes 8% and some other times it's 20%, you get large spreads. You get large spreads in the EDX measurement, and then your particle identification is limited. So this is not the only place where such large fluctuations are important. This also limits the detector resolution when for example, in tracking detectors, it limits the separation capabilities of particles in time projection chambers, and it also causes a spatial widening and secondary ionization of and with subsequent bremsstrahlung. You can imagine that if there's a large energy transfer happening, I mean, the impact on the original particle is, of course, also much larger. So I give you here a small recipe to compute how bad it is. And it's not hard to do. One takes the prefect of the Bethe-Bloch equation, which was 1/2 k times c over a times rho times c squared over beta squared. That's all the factors in front of the Bethe-Bloch equation. And that's, of course, so because that sets the stage. I mean, this sets the scale of the size of the energy transfer, because that's the quantity that gives you that's the dimensionful quantity. And you multiply it with the thickness. And then you divide this by the maximum energy transfer that we computed on the previous slide. And that's your shape parameter. If it is small, you get a very large tail. When is it small? It is small when your detector is thin. Because if your detector is thick, these processes still happen, but they happen for all the particles. And so it averages out, and therefore, therefore you see a similar energy loss for all the particles. If your detector is thin, for most of the particles, there are no such secondary delta electrons being produced, but for some of them they are. And in that case, you get a long tail. So thick absorber means that that the ratio kappa, which is the Bethe-Bloch prefactor multiplied with the thickness of the detector divided by the maximum energy transfer, is much larger than 1. Then the energy loss is Gaussian. We can build a good detector with good resolution. It may have other undesirable properties because it is thick, but at least the stochastics of the energy loss does not punish us. For thin absorbers, it has very strong tails. Here's an image of what happens. We have that you can understand what I wrote in the formula on the previous slide, with a proton here going through, and from time to time you can see it kicks out electrons, and those are then visible in this photographic plate. Now, the whole photographic plate definitely is a thick absorber, and these little delta electrons, they come at a certain rate, and this averages out. But if your detector material is very thin, then it becomes a matter of chance whether such a delta electron, these are these little electrons, that the delta electron interaction really takes place. So these are the things on practical side that we're dealing with when we construct the detector. Another, the same story. Atlas, of course, all detectors suffer from this problem. Atlas found a nice way of dealing with that in a specific case. Now, Atlas has a liquid argon calorimeter. So what that means is that you have material in the way of a muon that is subject to the stochastics of electron loss, as we've just discussed. However, in their case, this is an instrumented region. I mean, if you have this energy loss in a magnet is not a detector. Then the information is lost. However, if the muon goes through a calorimeter, you may actually see something. So you may actually record this ionization loss. That's what's shown for ATLAS, liquid argon calorimeter, in the middle plot. It's a calorimeter, so the ionization yield is given in picocoulomb. Coulomb is the total ionized charge, and it's calibrated to roughly 1 picocoulomb. Operates with 1 picocoulomb corresponds to 1 GeV. Look at the distribution of the ionization of muons going through the calorimeter. We don't measure muons in the calorimeter. We measure muons in the tracking system, but we can look at the ionization loss in the calorimeter. So where the arrow points is 5 GeV, 5 picocoulomb, 5 GeV. That's a 5% loss for 100 GeV muon. If this is not instrumented, that's actually a sizable loss, and it reduces the resolution. That's maybe a bit much to take for a beginner, but look at highly energetic muons coming from a hypothetical particle with a tera-electron volt. So that's that's a C prime, a hypothetical beyond the standard model particle that we may search for. It has 1 tera-electron volts in decays to 2 muons with 500 GeV, and those then traverse the ATLAS detector, and those then produce this stochastic energy loss in the calorimeter, which can be 5% or more. And because it's instrumented, we have recorded it, we have this information, and we can correct for it. And you see that the reconstructed distribution of the mass peak is steeper and is narrower if we put back this calorimetric measurement of the ionization. So in that sense, knowing all this, knowing the Bethe-Bloch equation, knowing the stochastics of the energy loss because of the delta electrons, knowing that you have a calorimeter in place where these unfortunate processes happen, and exploiting the signal readout in these calorimeters, we can correct back and improve the mass resolution in this particular case. That's a real life example. I wanted to mention it because it gives you a good idea what we're actually working on. I'm not in ATLAS, I'm in CMS. We don't have a liquid argon calorimeter. I can easily imagine a student working on this task. So that's real life. It does not quite fit the lecture. It's certainly far beyond what I'm going to ask you at the exam, where we'll just discuss basic properties of Bethe-Bloch. We'll not go that far. But I do want to connect the dots here. This is a beautiful physics application of basic processes. Another one, since we talk about real life isn't always fun. Let's talk about the penetration depth of heavy charged particles and the Bragg peak. That's a way to exploit the energy loss, in particular the 1 over beta squared term below the minimum ionization, beta gamma values of 3 to 5 for most of these particles. So in the Bethe-Bloch regime, most heavy charged particles deposit their energy in a relatively narrow region. The example to the right is 100 MeV protons on water. So the energy deposit here, these particles are MIPS, have a significant value for beta gamma. They lose a little bit, and then they get stopped because of the 1 over beta squared. Going back now, because I'm familiar with all of this, you probably aren't. We create the protons here in this regime, a few hundred MeV. They travel some distance, and once they have lost some energy, they lose it very quickly and end up being stopped, which leads to the so-called Bragg peak. This is the area where the incident protons thermalize. You need to take into account all these delta electrons, all the material effects, all the density corrections, and the nuclear corrections to really predict this. At the end of the day, the uncertainty in the position of the peak is roughly 10 centimeters. And that's, 10%. And this 10% uncertainty on the position of the peak comes from the absence of measurements. Currently, our institute is building a proton CT to reduce the uncertainty on the position of the Bragg peak. Why is it important? Because we can shoot those protons at people and damage tissue. That's not a good thing unless you have cancer at this location. And this is the basics of proton and heavy ion cancer treatment, which is carried out at Med-Austron. For example, you see an X-ray of the skull, and there's a computer simulation of the energy deposits with photons. With photons, you see that plenty of damage is done throughout large parts of the tissue, and using ions, which have a high value of C, and therefore have a very large DEDX and a pronounced, of course, a pronounced beta squared dependence from beta Bloch, can be used to very carefully treat very carefully and very localized cancer treatment. Now, I said there was a 10% uncertainty in the position of the Bragg peak, because you need to treat the volume. This uncertainty enters with the third power. So you have a 30% uncertainty on the true energy deposit. In other words, measuring the position of the Bragg peak really can save lives, because it really worldwide these measurements may improve the quality of future cancer treatment with heavy ions worldwide. So I think this is a very useful application of particle physics. Good. Next topic is goes beyond ionization. We've discussed ionization now, I think, to a very large extent, the mean energy loss, the beta Bloch region, the stochastics and everything. Now we move to Bremsstrahlung. Bremsstrahlung is the process depicted here. It's largest for lightest particle because it goes with the square of the acceleration, exactly a synchrotron radiation. Bremsstrahlung is the interaction of, for example, an electron in the Coulomb field of a nucleus. So it gets accelerated a little bit, and because of its acceleration, it emits a photon. It's important to know, for detector applications, it's important to know that Bremsstrahlung is the dominant source for energy loss. Why is it so? In lecture 1, we calculated very carefully the energy loss of an accelerated charge and the power of the total power of the radiation due to synchrotron radiation, or due to the acceleration, goes with q squared and v dot squared. So v dot squared is the square of the acceleration. Now, we know that because of Newton's first law, m times v dot, m times acceleration is proportional to c times e. It's important that this c now is a coherent interaction. The electron exchanges a photon with the nucleus, not with the proton inside the nucleus, and also not with the quark, but with the whole nucleus. You have coherent interaction of the whole nucleus, and hence the acceleration is proportional to CE. And you don't have individual accelerations from individual incoherent interactions with the constituents of the nucleus. We are not by far in the inelastic or deep inelastic or whatever regime. This is completely elastic, long wavelength, if you compare with our discussion in the second lecture. Now, because that is so, we can replace the V dot by C over E divided by M. That means the dissipated power by Bremsstrahlung is proportional to C squared over M squared. C squared because it's in C squared because this is a coherent interaction. Now, Bremsstrahlung grows with C squared, all right. The other thing is the acceleration is force divided by mass, and hence the Bremsstrahlung is the rate of Bremsstrahlung when you compare muons and electrons are different by a factor of 40,000, because the muon to electron mass ratio is roughly 200 and it enters squared, so 40,000. That means it's relevant Bremsstrahlung is relevant for electrons. It's very small for all the other particle species. Muons, it's already almost negligible. Let's go back. Let's go back to the full Bethe Bloch. That's Bremsstrahlung, radiative losses. They are only relevant for the highest energies in almost all detector applications for muons, from colliders at least. This is completely negligible. For electrons, it's important. Now, we don't do a careful and comprehensive calculation here because one needs to take into account dielectric suppression, polarization, which is the polarization of the medium for low energies, coherent scattering, and all the shielding effects that are relevant in atomic physics. We do average and simplified treatment that's, however, completely sufficient for detector applications. I'll stop now. We'll do this after the break. It's 1. We reconvene at 1:30. What we put in is the last thing I want to say is that the energy loss per unit length is more or less to very good approximation proportional to the energy of the particle itself, which leads to a simplified description in terms of radiation length. And we look into the detail and the material dependence of the Bremsstrahlung effects after the break. I hope I get my pencil to work and we can do some of these calculations at least. But after this short intro to the Brem, we will make a break. And I stop the recording.